and communication protocols for connected and autonomous vehicles. Peter's going to be talking about cybersecurity and communication protocols for autonomous vehicles as an advancing group of technologies. He'll present the present state of the technology, future developments, and with particular reference to a project on connected autonomous vehicles being led by the University of Ottawa. Peter, I was delighted to see that you gave a brief form of your bio.
Well, it always is brief because I can't say it all.
Yeah, well, you've a combination of living long and doing much. Your bio can cover a lot of ground. Peter has a background as a scientist, business manager, entrepreneur, domestic and international bureaucrat, executive, diplomat, management advisor, and academic. And today he's affiliated with the Telfer School of Management and the Faculty of Engineering at the University of Ottawa. Peter's a pioneer in the commercialization of AI and is actively involved in ethical and policy issues related to it, especially as a member of various committees such as the IEEE USA Artificial Intelligence Policy Committee, the IEEE Standards Association on AI and Ethics Committee, Fortune Magazine's AI Advisory Board, and Harvard Business Review's AI Advisory Council. Peter has an extensive background at the forefront of scientific and technological breakthroughs around disruptive technologies and their impacts on society. And he also writes frequently about AI in editorials and policy organizations. Well, Peter, take her away. We're honored to have you.
All right. Well, thank you, Steve, for that flattering introduction. And I know all of you know me at this point, so that's really quite nice. I might just mention there'll be an op-ed published with my colleague Ellie Fahy next week in Research Money, and it will be on a rather provocative topic called "Can Democracy Survive Artificial Intelligence?" So, with that as a background, let us get on to the present. And I might point out, I slightly changed the name of the title of this slide from what was advertised on our website. And I came up, I guess, with a bit of a pun. Didn't realize it till I read it over. But I now say the cybersecurity and communications protocols, the keys to connected and autonomous vehicles. So I guess that sort of makes it sound more related to the vehicles as well. So let me begin. I will. Who's in charge of? Like, can I change the slides? No, I can't. Can you do that, Steve?
I just did, so you
Yeah.
can
Okay.
instruct me accordingly.
Yeah. Okay. Go back to the table, the agenda, and this is the things I'd like to talk about. I'm going to start with a few definitions to give us a clear understanding of where we're coming from. Then I'll discuss something called the technology readiness levels. This is used in both Canada and the United States in particular for ways and means of developing and assessing a state of a technology from idea to implementation. I'm going to give some examples of the autonomy is coming in the sense of surface transport with some specifics from different organizations and deal with the technical challenges. There are five levels of autonomy with respect to service vehicles, and we'll review what those are. And then we'll also look at where AI fits into this equation of autonomous vehicles, and then an overview of the what I call the site cab project, and that'll be deep unpacked when we get to that part of the agenda. So next, please, Steve. So here are the classic definitions of what we might call a connected vehicle and an autonomous vehicle. And you can see the difference by just simply reading this text. The basic things is that the connected vehicle uses wireless technology to exchange information, improving its safety, efficiency, and convenience. The autonomous vehicles, on the other hand, these are the ones without drivers. They're not driver assisted. Their intent is completely autonomous. So we'll deal with these in discussing how to get to those in the course of this little discussion. Um, Effectively replacing the need for a human driver in certain and or all driving conditions is the intent of the autonomous vehicle. Next, please. So these are terms you're no doubt aware of. Cybersecurity is to give the definitions in a cyber attack. What a cyber attack is usually trying to do is, of course, aim at accessing changing, or destroying sensitive information, and then making use of it for any nefarious use or cause. A successful cybersecurity posture has multiple layers of protection spread across the computers, the networks, the programs, and the data that one intends to keep safe. So, a cybersecurity is more than just the data and the programs. It's much more of a whole holistic approach. Next. And looking at communications protocols, here are some examples and the key functions of communications protocols. Basically, on the functional side, it's data formatting, error detection and correction, message acknowledgement, and flow control. Next. Now, there are various terms that are used in the evolution of vehicle to vehicle transportation. So we have V2C, V2V, which is vehicle to vehicle communications, vehicle to infrastructure communications, and vehicle to network communications. So I'll use these acronyms with the V's from time to time. So think of vehicle to vehicle to communication, vehicle to infrastructure, and vehicle to network. Next. So here are the 5 levels of automation. This has been established through an international arrangement through an organization that used to be like it had each of those letters. SAE stood for a word. The acronym has now become the name, so it's SAE International. Somewhat like IBM used to be known as International Business Machines, and now they're just IBM. So here are the 6 levels. One level 0 is as we have all of us would probably has our vehicles are today. There's no automation other than basic cruise control. And some people might now, of course, I guess I wouldn't call it automation, but with the cameras and so on with lidar, you can see certain things, and so there's some sensitivity to range detection, but it's still not automation per se. And the objective ultimately is to get to level 5. The project that we're dealing at the University of Ottawa is actually working at the technology development level 4. And so we're planning to get, well, you'll see more about this when we get onto discussing that project. But level 5 is still only concept. There are some tests going on now in the States, in Phoenix, for example, where Waymo is running a level 4 type cars in a controlled taxi environment. Next. So here's this technology readiness level concept. It goes to 9. The other one went from 0, which was just showing it's sort of different ranges here. That's all. Given links, as you noticed, for every slide, I think that has anything relevant to looking up. So you can read what these all are, and just you can see the basic idea starts at 1 or 0, and it grows over time. And this is used by if any of you work with national defense. The Defense Research and Development Canada uses this technology readiness level system as well. Next. So why do we need connected and autonomous vehicles, CAVs, for example? Well, their aim is to solve real-world problems in transportation, safety, energy, and accessibility. And here are some of the examples on each of those. Safety, 94% of road accidents are due to human error. So we can reduce if we can increase the safety of a vehicle by reducing human error, we could, one example is to take the human out of the loop and make the system run itself. This, of course, is fraught with all kinds of other activities of dealing with traffic, dealing with other humans in passengers in the car, crossing the streets, etc. I mean, this is one of the most complex areas of applying AI, I would argue, far more so than in the large language models, because we're dealing with real world 4-dimensional systems here in terms of spatial as well as time, and so many different things that are unpredictable, or at least unpredictable in the sense of when it might happen. We know it could happen, but when it happens. And so there's a lot of dynamics, as you all know, when you get stuck in traffic jams or caught in traffic accidents, it can be a real headache. So safety is certainly number one reason for going this way in terms of trying to make autonomous vehicles. Efficiency and congestion reduction is another important reason for looking at autonomy because that way the system can try to control the traffic flow and adjust it accordingly. And next, please. Accessibility, obviously, there's a variety of accessibility issues as with vehicles they are today. So we want to design and develop the future vehicle that can allow for elderly, disabled, and so on, other types of entry and egress and entrance of these types of vehicles. And connected systems can integrate with public transport for seamless first mile and last mile services as well. I mean, you often people who live on the on suburbs, for example, will take a commuter bus from the entire interior of the city direct to a drop-off point in the suburbs, and then they might go to the countryside from there. Well, you could integrate the vehicle systems, both the public transit and your car systems. And if you've got automated cars, you can actually have your car call to come and pick you up at whatever point your office would rather not, because then you're down in the core of the city, perhaps. So you'd have it pick you up at the end of the transit line. Then there's economic productivity benefits as well. And not only does it reduce the costs of, you know, it reduces accidents and in doing so, you reduce the injuries, therefore to the less cost to the medical system, and you reduce the requirements for replacements and have an impact on the repair shops and garages that repair vehicles. And in fact, with autonomous vehicles, it's going to be even more difficult. I mean, those of you who already have electric vehicles will recognize they're not the kind of car you could repair in your garage as you could 30 years ago, if you were so inclined. And nowadays, you probably need more equipment and value than the cost of your car just to test your car. So the testing and repairing of these types of vehicles is going to become far more complex, although durability is being increased, so the less frequent visits. And next, please, Steve. There's economic productivities and freight and all that kind of stuff too.
It's not, sorry, we're not advancing.
Oh,
There we go.
okay. Well, one question one might ask are our connected vehicles just a transition to autonomous vehicles? So a connected vehicle, let's say they're not exactly because the connected vehicles and autonomous vehicles are complementary, but distinct paths in transportation innovation. The connected vehicles are more than a stepping stone to an AV. They embrace safety and efficiency even without autonomy. And AVs can operate without connectivity, whereas full autonomy without connectivity leads to very limited use cases with closed environments like in mines, in farms, in mail sorting facilities, that sort of thing. You can have full autonomy without connectivity. So there's a range of connected to autonomous in terms of the actual vehicle and its what it can do and how it can be applied and in what sort of work environment. Next. Now, here are some principal differences between connected and autonomous vehicles to give you a better understanding. And I've done it against a few criteria. So their role, the time frame as to what we're talking about in deployment, dependencies required, relationship, and the transition role. So you can read those. I need not raise any, repeat everything here, but if there's any questions on this, don't hesitate to ask. And next, Steve.
I just
And
have
if
a
you have,
question, Pete.
yeah.
I just have
Mhm.
a question. Yeah. So, connected vehicles already widely deployed. So we're defining that in terms of being connected to the internet or to manufacturer systems and such,
Yeah, to GPS.
as opposed to connected to other vehicles. Is that correct?
Correct. Correct. Yes, connected to the infrastructure,
Yeah.
or
Okay.
call it the infrastructure, outside the vehicle and not other vehicles.
Yeah.
I mean,
Okay.
you are connected to other vehicles in the sense of if you're talking on a phone, a wireless phone, but that's not the same as an autonomous vehicle by any means.
Right. And in traffic information is also sort of indirectly vehicle to vehicle, but
Yes,
okay,
that is true.
I got the distinction. Yeah. So widely deployed in certain use cases.
Yes, not widely deployed in a universal sense.
Yeah.
I would suggest that then we're just talking about connected. Now here, let's go talk about autonomous. Um, well, autonomy is already coming, and I just sort of go back about 10 years to give some examples and bring it up to the roughly the present. And you can just scan through these and see the dates. I mean, it's basically going forward in time, and we're continuously seeing, as you can read, increasing sophistication in what is happening with these types of autonomous vehicles. And in fact, some of you might remember back, I would suggest it was in the 1980s, if not even a little before that, that DARPA began running a program at primarily American universities to build autonomous traveling vehicles. And they ran it as kind of cross country races, as in races in the desert. And there were many, for about a decade, I think that program ran. And of course, the university engineering schools and computer science groups and others involved did get to a point where they got some pretty good autonomous vehicles that could race and run a course in a desert kind of situation, then in a court, and then build a course that goes around and pylons, etc. And ultimately, they led to some tests that started happening in the West Coast in California on the roadbed. So we're now at that point today. Next, Steve. And you can see as we go forward here, there's all these different examples. And I just provide these as examples, and more information on these can be gleaned if you wish to read the material after the fact. Next. Oh, and yeah, some more examples right up sort of into the present. This is interesting. The last one, as some of you know, or all of you would know, Hong Kong is, of course, not part of mainland China. It has a 50-year agreement after 1997, I think it was, in the handover. And China, the mainland, is trying to find ways of closely integrating with Hong Kong and other areas in that region of Guangzhou. And so this is an example of a operator who has taken a autonomous bus and so a robo bus as opposed to a robo taxi, and it's launched this in the overall Guangzhou plan for deepening cooperation between Hong Kong, Macau, which is also a former Portuguese colony that was transformed. At 500 years, it was under Portuguese control, and it was passed back to the Chinese in it was the year 2000. So they wanted to integrate these, and these are all very active regions of the Chinese economy. Next, please. So the primary technical challenges in developing autonomous vehicles, there are a number, and I haven't put these in any specific priority, but obviously perception and sensing would probably be at the top of the list because you can't be autonomous in an environment without sensing it. So that's number one. But the key issues, I generally have identified a few issues for each of these. Sensor limitations, as we get more and more more and more quantum sensors, for example, we'll get much better sensing and reliability and even fragmentation of time and therefore data rates. Then the sensor fusion. That is, of course, multiple sensors are required to understand the environment you're moving in. I mean, we are the sensor system in an automobile. We use our ears, our tactile skills, our vision. We probably use our emotions to some extent. If you blow the horn, it's because either you're mad at something or somebody is, maybe a danger is cropping up. So we are the sensor system in the car. So now we're trying to give some of those sensings to the vehicle itself. That's a way to sort of think of this. And that's about the sensor fusion issue. And then critical object detection and classification. This is where, in effect, millions of scenarios are required. And they won't all be, I mean, they'll all be, let's call it possible scenarios, but that doesn't mean to be all the scenarios. For example, I mean, here's a scenario, and I thought of this because on Halloween, a friend of mine did this. He was dressed in a large Tyrannosaurus Rex costume, stood about 2 meters high. Well, when walking across the street, If an autonomous vehicle saw them, it wouldn't know that there was a human inside a Tyrannosaurus costume. So there's a scenario. They got to think about these scenarios for autonomous vehicle. Oh, good to see you, Richard. So that's one of the other key issues. Next, please. Now, location and mapping. Obviously, if you're autonomous, you've got to navigate through some three-dimensional space, and so this becomes a very big issue when you deal with digital high definition maps. I mean, many of you, if not all of you, navigate around sometimes in your cars with your GPS. Well, the GPS maps are not nearly as detailed at the granular level as we need for these types of autonomous vehicles. So there are key issues there. And localization, small errors in the localization can compound over time, leading to serious navigational mistakes. And, keeping up to date in a city. I mean, cities have roads that close every day and new roads open and accidents happen and so forth. All that kind of data has to be made of real time available inside these spaces that we're going to have these automated vehicles. And then the prediction of human behavior. That's another one of the most challenging dimensions to thinking about building autonomy into a vehicle that can travel on a roadbed and hit people if it's not under control. And we need to understand more about the human behavior. In fact, on this university project, we have people from this social sciences who are part of the project. Key issues, of course, are the unpredictable behavior of humans, and that we all know what that's like because we're all humans. And you can see body language, eye contact, and informal rules. They're very hard to implement in a machine. At least they are today. So those are some of the primary technical challenges. There are more. Next, please. Planning and detection, decision making. I mean, it's planning a course, it's planning a route. It's doing this in a active and a real-time way. So it's proceeding ahead, it's planning. So key issues are the multi-agent complexity. AIs must coordinate with other vehicles and agents, often with limited communications. And good examples are the ethical dilemmas, no-win scenarios, dynamic environments where roads, traffic, and the various obstacles are constantly changing. These are very important issues to deal with if you're going to have a autonomous vehicle. And then the real-time computing and systems latency. Clearly, that's very important. You can't have something that's operating any of the components that are required to be at the same time. They can't be working at different delay times. Everything has to be absolutely synchronized. And that too is a massive engineering challenge. And finally, key issues are hardware performance requirements such as power, energy efficiency. I mean, a lot of this is wireless. I mean, the car can generate energy, of course, from its wheels rolling, or you might have a solar panel on the roof, but you can generate some amount of energy from the moving vehicle. But sensors are basically wireless, so they need power, and that power has to come from somewhere, a battery or some other source that might be wired into the vehicle itself. Like I'm sure the lidar is wired to the vehicle's electrical system. Okay, next, Steve. One more here. Oh, this is it. Yes. Um, so robustness in adverse conditions. Clearly, I think you would understand that as in our weather systems we have here, and secure and resilience of the system that shouldn't be able to be hacked and so on. That's how you can appreciate, and that's one of the things we were very concerned about in our research lab. And the edge case handling and generalization. Millions of edge cases, rare, unusual, unexpected situations, such as my dinosaur metaphor. Key issues is lack of data and generalizations. ABs must perform safely in new, unseen environments without explicit programming. So these are some of the challenges. One more, next one, Steve. And then there's the valid verification, testing, and validation, proving these things are safe. Key issues are scenario coverage. As I said, millions of scenarios over millions of miles of real world testing is required. Infrastructure and integration challenges. Clearly, not everywhere works the same in terms of the infrastructure. Road beds are different. Key issues that a vehicle to the X communications, that is vehicle to everything, can help, but we don't have that kind of infrastructure yet. And mixed traffic. I mean, AVs must coexist with aggressive, inattentive, or rule bending human drivers. And that's very highly unpredictable. In fact, I can anticipate there'll be some human drivers that will want to run into an autonomous vehicle just to see if the autonomous vehicle how it will respond. I mean, I'm sure that will happen if it hasn't already in even tests. Next. Now, here's a summary of the role of AI in autonomous vehicles. And you see, I've defined it by the functions, basically drawing from some of those things we just were looking at in the challenge context, where AI fits into it, and what kinds of AI techniques are being applied to address that function. And I don't need to read these. You can see these, and there's some acronyms in here that I didn't actually provide an acronym list, but you can easily decode them by a web link if you look. Okay, next team. We're getting towards the end, I think, before they get to the case of the university project. So technical challenges in getting autonomous vehicles to level 5. Now, this is the technical challenges to level 5, not just to autonomy. But previously, we've been talking about going from up that scale of going. Now we're dealing with level 5. Some of what we just looked at, of course, is level 5 issues too. But perception in unrestricted or unpredictable environments is a serious problem. Sensor limitations and long tail edge cases. And then there's the handling of adverse weather conditions. And next, dependencies on high definition maps. This is somewhat similar to what we just discussed, I guess, earlier, with a little more detail, looking at the level 5 requirement. Also, decision making and ethics in complex social scenarios is a problem. We haven't talked about ethics yet, but clearly the need for AI systems to not go rogue would be characterized as having some degree of ethics. I'm with my colleague Ali Fahy. As some of you know, we write a lot about AI op-eds. We write a lot in AI op-eds about integrity and ethics as it relates to both the developers and the use of these types of tools. So decision making and ethics in complex social scenarios is a big issue to deal with, and this is where social science is an important play in this. Next. Real-time sensor fusion and processing problems, like I was saying before, and the cybersecurity risks that people will either hack systems or try to hack systems, or there could be failures. And we have to understand what could fail that could cause, a cascading effect. In order to prevent that from happening, we need to appreciate what are possible. Next. Now, of course, there's a global variability in a variety of areas. I mean, regions are not the same. Road beds are not the same. Speed limits, signage is not the same across the world, and we're building universal vehicles. So, how do these adapt? I mean, this is part of the core issue I have with ethics and integrity. Ethics varies across various cultures. Integrity is common to all cultures. So, how do we find common ground when we developing systems that are actually are challenging human activities and the way of humans think? And then there's, of course, overlaying all of the technical and social dynamics, there's the regulatory and legal frameworks that need to evolve around this. And currently they're very ambiguous because we're just learning how to do these things. Prior to this event of our talk today, Steve and I were talking about a trial with the WAMO in Phoenix. And I mean, that's an example where, it's cities that are adopting the trials. It's not states. It's not a province or a territory. It's not a country. At this point, it's just cities, and it tends to be cities in relatively good climate conditions, such as Phoenix. It doesn't get heavy storms very often. It's generally mild weather, so on. So we're going to be over the next 10 years, I'd say, we'll be learning more and more about how to actually construct, operate, and run an infrastructure that is based with autonomous vehicles. Next. So the challenges again, this is a perception issue. These are the challenge issues, and I've summarized here the why it matters. Next. So let's turn now for a few minutes to a project that's led by uOttawa. There are three universities involved, but let me begin by just discussing that the University of Ottawa Faculty of Engineering decided to create an innovation center around transportation. And so this project I'm going to talk about is now the first major project within this new innovation center. So it's called the Smart Connected Vehicles Innovation Center. It's contributing to autonomous vehicle innovation. It opened about 4 years ago at the uOttawa campus in Canada North. The reason both Carleton and the University of Ottawa have got engineering facilities out there is that both universities felt it was important to reach out to the technical community of startups and more mature companies that tends to dominate in West End of Ottawa. And so Canada North was a natural place to do that. The center focuses on research that solves vehicle and network problems regarding their connectivity, their physical and cyber security, and the decision making and sustainability of the environment they are operating in. It brings together experts from various fields, as I've mentioned, and on our project at the current stage, we have a variety of people involved who are social scientists, economists, ethicists, and compliance specialists. We have faculty of law, for example, involved, and we have decision makers alongside engineers and computer scientists. Decision makers, as in business decision makers, people who are deciding what functions and so on will have to be part of a solution. Next.
Sorry, Peter, which universities other than uOttawa is
Yeah,
involved?
I'll cover that all in a few
Oh, okay,
minutes. Yeah,
okay,
this is just introducing the lab, and
okay.
then I'll
Thank
talk
you.
about the project. So here's the major two lab initiatives. I just mentioned the site cab one. We'll go into detail in a moment. So the center is the home for the training and research in autonomous vehicles for reliable service in air and land. And this is the acronym. And three universities are involved in that, and it's funded by NSERC, National Science and Engineering Research Council, which is a national granting council. And so this is just a quick summary of what the traversal program is about. And the site cab project is what I will talk about. That's the second one, and it's much bigger project. So it's a collaborative and interdisciplinary project to enable smooth integration of connected and ultimately autonomous vehicles into the evolving transportation ecosystem in Ontario and beyond. And why is it Ontario and beyond? Because the principal public funding for this project is from the government of Ontario. And the three universities involved are the government of Ontario, are in Ontario, and those are led by uOttawa, University of Toronto, and Western University. University of Western Ontario changed its name to Western University. So it's dealing with a couple of research questions laid out here: the development of ethical and reliable communication protocols integrated with security by design solutions, along with intelligent, user-friendly, and legal-aware decision support systems. So this is the objective. It's a 4-year project, multi-million dollar, and we have 10 business partners currently, and I'll explore that a little bit more as we go along. Next. This is that technology readiness level, TRL level thing that I showed before. And the arrows here are the first arrow on the left is where we're at today. Well, this project has been running almost for a year now. But this first year of the project is ramping up. I mean, you get an award that could come at any time during the year. Well, our academic years would typically start in September or in January. So we got this award in September. So it took us a few months to start even planting and getting because it's all this research is grad student stuff and postdoc stuff and professors as well, research. So we had to plan, we laid out a very detailed plan to win the work, but now we have to populate it. And of course, the professors and administrative people are there to do it right away, but the students aren't there. They have to be assigned. I mean, you're going to do a PhD. What are you going to do it on? Well, we have this project. This part of the project needs to be examined in detail. Are you interested in doing this? So you'd have to negotiate all these things, or assign it to your postdoc or your grad student. Anyway, that's why it takes about a year to get these things ramped up. So this is the start point, and we're anticipating reaching level 7 by the end of this project. And hence, that's the interest of our business partners. One of our business partners actually interested in beyond 7. It's the Canada Post. They're interested in it because they have large facilities where autonomous vehicles would be a great assistant running around inside sorting rooms and such things as that. So here are the components of the project. There are 4 main ones: cybersecurity and cyber safety, ultra fast and agile communications, human factors and trust, factors in CAB technologies, and legal and social implications. Next. This is a breakdown of the academic pattern of this project. So here are the 3 universities. This is, as I said, led by uOttawa. So you can see many of the people here at uOttawa. I've got a little color code for the professors as to what their specialty is. And so most of them are, in the engineering faculties of these 3 universities. But we also have people in the law as well as in our business school. And each of these people have people within their groups. And all of these people have students as well, postdocs, PhD students, and master's students. So you can see that we're even with 10 so professors, you suddenly have 30 or 40 people on a project. Next. Oh, and the tentative just means we're. If you go back, please. Some of you probably knew Hussein Mufta. Hussein passed away recently. Just about 10 days ago, I was asked to be one of 7 speakers as a memorial for Hussein at the Faculty of Engineering. I worked very closely with Hussein from 2009 until this year. He was a co-PI of this project. He was one of the most respected professors at the university in terms of his manner, I respect in that sense. He was extremely accomplished as well. He had 3 Canada Research Chairs, Tier 1, each one a different discipline. Anyway, let's move on. Jonathan Kaloff is a colleague of mine who is in the business school, and he will be joining us shortly. Here are our 10 business partners. We have 1 from Alberta, 1 from California, and all the other guys are all local. Some of you may know of Area XO. It's actually operated by the city of Ottawa. It's a test bed out in the West End, situated on the edge of the experimental farm off Woodruff Avenue. And these are various companies. Already we've filed a patent, co-filed with ThinkRF this first year, just filed it a few days ago. And that's in collaboration with our Intellectual Property Office of the University of Ottawa and ThinkRF. It'll be shared intellectual property with that company. So any questions on these things, we can talk about these in our discussion group. Next, please. We have an intellectual property strategy. I won't go into this in any detail. I just provide this as for follow-up if you're interested in reading it. Universities tend to have varying ways of how they deal with intellectual property. They have a central organization that typically has a patent lawyer as a head of that group, as is the case at uOttawa. And we work together with our business partners in looking at what can be patented and not patented and who has the rights to patent, et cetera. And I would suggest I'd just move on from this. You could read that if you need it, if it's of interest. We also have a commercialization strategy. Much of this stuff that deals with commercialization, the patenting, and so on, the administrative of the workshops and conferences that we do hold. These are some of the things that I'm responsible for. So the commercialization plan basically deals with how we're going to move the output from this project into the private sector for uses in developing products and services that may come from their offerings. Next. And more steps in that process. Classic backroom business stuff. Next. We also have a webinar and seminar series. And because we have these two major projects, Transval and the site CAV, we want to try and share for the student benefit of both parties at all the universities are participating, opportunity to get involved in these webinars and seminars. So I'm looking at the coordination and lining up of speakers for this sort of thing. We've already had two seminars on this, and we've had one workshop. We had a workshop. In fact, Morteza was a judge at that workshop. We had 21 poster papers, and I organized a team of local judges with excellent experience to be a judge at such a graduate level presentation. Maybe you might say something about that. I had a good discussion, Morteza. And events will likely run on a bi-monthly basis, and we have another 3 years of the project starting in January. Next. And this is the workshop I was just referring to. We had our first workshop in June, and we had a hackathon. I haven't had the results of that yet. It was very recent, but we have a hackathon that we actually have the students broken into teams, and they compete against each other around the technology that we're working with. So this is a really interesting way to yeah, the first workshop. Oh, that was the workshop. Yeah, not the hackathon. Yeah, the hackathon. We also are working with the cyber range at University of Ottawa. It's the cyber range is a massive gift from IBM. It's one of only I think they have 7 cyber ranges in the world, and it's quite a sophisticated environment for doing cyber simulations, particularly in regard to security. Next. In addition, I lead a youth outreach initiative within our project. And by example, this is of course designed to try and attract young people to STEM. And there's a strong emphasis in our efforts, both mine and my colleagues, to attract young women to this area as well. And in fact, we have several women who are professors who are part of the team. And they too are very active in the STEM dimension, particularly for women. We're looking at students and postdocs are encouraged to consider, participating in these events. We in the past, for example, with YSense and a 5-year project I was the executive director of under Hussein Mufta, we would do outreach at some of our museums because the museums would allow the university to have a public outreach in their facility on, say, a Saturday and a Sunday, when lots of young kids get to go to, and parents, particularly if you know single parents who bring their kids to the museums on weekends. Next. You got the next there, Steve? Yeah, that's it. Oh, must have been an end one. Can you scroll right through? Yeah, there's the end. There is an end one. I guess that was the last one.
So okay, there we go. Sorry.
Oh, there we are. Yeah, summary. So this is the summary of the talk now. So connected autonomous vehicles are shaping the future of vehicular traffic. I do believe that will be the case. I don't see any reason why there should be a massive, social pushback against this type of technology, because it's going to vastly improve the safety of our roads. Not initially. I think there'll be people, as I said, trying to crash into these cars on purpose, and these cars will probably crash into other people-populated cars that aren't autonomous, not on purpose, but by fault. So there's going to be a learning period, but we've seen this before with other technologies and products and services. The cybersecurity and wireless communications protocols are absolutely critical components to any connected and autonomous vehicle and connected and autonomous vehicles. And AI plays a pivotal role. I believe autonomy at the level 5 demands a great leap in our ability to do really high quality pattern matching, pattern recognition to human level judgment. Otherwise, these systems shouldn't be introduced even into the public. So we I feel this is a global issue. I mean, it's not just Canada, North America, or U.S. working on this problem. Many countries are working on this, and there's lots of collaboration at the research level, particularly among academics. And they also meet and talk with each other at international conferences. And so this SiteCab project aims at achieving level 5 autonomy, at least in principle by you know 3 years from now. So that'd be not too far away. And next, I think is the last slide.